Okay, so we have seen already in previous lectures special types of elements, special types of ideals, and we have seen some special kinds of rings. We know that fields are very special rings, and we know we have this property of integral domain. We've seen that's very useful. It rules out all the bad stuff like zero divisors and nilpotent elements. Okay, now I want to introduce some even more specific types of rings. So we have fields. This is contained in integral domains. So every field is an integral domain, and we want to insert stuff in the middle. So every field will be a Euclidean domain once we define what this is. Every Euclidean domain will be a principal ideal domain once we define what that is. And finally, every principal ideal domain will be a unique factorization domain. And every unique factorization domain is an integral domain. So this picture is good to keep in mind, and it's good to keep in mind that all of these inclusions are strict. So for every one of these, you can find an example that is not of the type to the left. So you can find a unique factorization domain that's not a principal ideal domain, and so on. All right. So let's define these. So let's start by defining principal ideal domain. This is easiest to define. So an integral domain R is a principal ideal domain. So this stands for principal ideal domain if every ideal in R is principal, that is generated by one element, i.e. for every ideal I in R can find X in R such that I is equal to X. This ideal generated by X, by definition, this is the set of X times R with R in R. It's the multiples of the element X. So this is a generalization of what we did in the ring of integers. We took a number n, and we formed the ideal nz consisting of integer multiples of n, all those integers divisible by n. Okay, so as I said, this is we got inspiration from what we did in the case of the integers, and so an example is the ring of integers Z. This is a principal ideal domain. One has to show this, but it is not hard. And then the other fundamental example is f bracket x for f a field. This is also a principal ideal domain. Now, these are in fact both examples of Euclidean domains. So a good way to prove that these are principal ideal domains is to first prove that they are Euclidean domains, and to show that in general that every Euclidean domain is a principal ideal domain. So let's go on and define Euclidean domain. Okay, so we first have, a Euclidean domain is modeled on the Euclidean algorithm in the ring of integers, or also on the Euclidean algorithm for polynomials with coefficients in a field. So the usual long division algorithm of dividing one polynomial by another. So a Euclidean division function in a ring R is a map D for division that goes from R to the non-negative integers, such that for all A, B in R, with B not equal to 0, I can divide A by B and get a remainder that is smaller in the sense of the function D. So there exists a quotient Q and a remainder R such that A is equal to B times Q plus R. With this remainder, it has two possibilities. Either the remainder is equal to 0, or this degree or Euclidean division function, when I apply it to the remainder, this gives me a non-negative integer. That non-negative integer should be strictly less than its value on the quotient Q. So this Q and R are called quotient and remainder for obvious reasons when you write this. And then an integral domain R is called a Euclidean domain if R possesses a Euclidean division function. Okay? And then as I wrote up there, and as I was talking about in the examples, a lemma is that every Euclidean domain is a principal ideal domain. Okay, so let's see some nice properties of principal ideal domains. So I already advertised these as a motivation for considering the notion of principal ideal domain. So one is that in a PID, every irreducible element is prime. So in a PID, irreducible if and only if prime, because we had seen before that in an arbitrary integral domain, every prime element is irreducible. Second nice property is that in a PID, every non-zero prime ideal is maximal. Okay? And finally, in a PID, we have unique factorization. Have unique factorization So what does this mean? Well, so let me tell you, and then we will use this to single out an actually larger class of rings called unique factorization domains. And in the diagram that I had at the beginning, all the inclusions going from fields to integral domains, that's the last one that we have left to define. So as a precursor to the definition of unique factorization domains, I have to tell you what it means for two elements to be associate. So if A and B are in R, we say A and B are associate if there exists a unit U in R cross such that A is U times B. So being associate, this is an equivalence relation. An example is 5 is associate to -5 in Z. And I can now tell you why do we want this notion of associate. We don't want to say that 5 or we don't want to say that 10 is 2 times 5, 10 is -2 times -5 are two different factorizations of 10. We want to say that we have unique factorization in the integers, as we know from the fundamental theorem of arithmetic. And we want to say, yeah, but all that's going on there is we just took the 2 and the 5 and we multiplied them by -1. And this is, so here, and this is because 5 is -1 times -5, and -1, this is a unit in Z. So we want to kind of avoid this trivial confusion that can arise from these units. Okay, so now we come to define the last class of rings, unique factorization domain. So an integral domain R is called a unique vectorization domain, or UFD, if we want to say that every element has a unique factorization into irreducible elements. So how do we say this precisely? If for all R in R with R not equal to 0 and R not a unit, so we want to throw away those, one has the following two properties. So first, the existence of a factorization. R has a factorization R equals P1 up to Pm with Pi irreducible for all I. And secondly, we want to say that this factorization is unique in a natural sense. So that's the uniqueness property. So if R equals Q1 up to Qn is a second factorization, then we want to say that basically they're the same, but we have to be careful about a few things. So we have to, what do we have to be careful about? We have to be careful about, just as in the integers, with reordering the factors. And then also remember, in the integers we had this issue of plus and minus 1 of the units. We have to be careful about that. So that's this
is taken care of by this relation of associate that we defined. So if R is Q1 up to Qn is a second factorization, then first of all, the number of factors is the same. Then m equals n, and up to reordering, Pi is associate with Qi, which remember means that Pi is equal to Qi times a unit. Okay, so now let's end by doing a little compare and contrast between unique factorization domains and the notion that we just defined previously, that of principal ideal domains. So compare, contrast PID versus UFD. Okay, so let's make a little table. So we have PID, UFD. Okay, so PID, we have seen that we have irreducible, X irreducible if and only if X is prime and X not equal to 0. And this is true also, so this is also true for a unique factorization domain. In a UFD, in a PID, we have seen that every non-zero prime ideal, every non-zero prime ideal is maximal. This is not always true in a UFD. And finally, so this is a downside of UFD over PID. We lose this property that every non-zero prime ideal is maximal. On the other hand, every polynomial ring over a field, so for example, f bracket x1 up to xn, a polynomial ring in n variables, is a UFD, whereas for PID, only polynomial ring in one variable is a PID. So f bracket xy, not PID. Okay? So to sum up, there are some properties like irreducible if and only if prime for elements. This is true in both PID and UFD. Every non-zero prime ideal is maximal. This is true in a PID, but not true in a UFD. On the other hand, an advantage of UFD over PID is that it holds for much more general rings. For example, all polynomial rings. So UFD satisfy a bit less than PID, but many more rings are UFD than PID, and this is especially useful when you go on to study the interaction between algebra and geometry in the subject called algebraic geometry. And just to end, let's just give an example of what we said here, that it's not true always in a UFD that every non-zero prime ideal is maximal. So let's take the example I've given here of a ring which is a UFD but not a PID, f bracket xy. So f, example, f a field, R is f bracket xy, is a, this is a UFD but not a PID. So let's see some ideals to see this. So the ideal I generated by x and y is not principal. That shows that it's not PID. This ideal I is generated by two elements but cannot be generated by one element. And on the other hand, if I look at the ideal J generated by X, this is a principal ideal. This is prime and non-zero, but not maximal. Okay, so the second property also by this table is something that cannot happen in a PID, but now I've given an example that it can happen in a UFD. Okay.